Hey everyone, in this video I'm going to be going over the solutions to the fourth and final free response question practice test from your folder. Some of these questions may look familiar to some of you, and I think that's because we did some of them earlier in this year as just part of our regular class, so if you think some of these look familiar, that's probably why. But anyway, let's go ahead and go over the answers again. So for the first question, we're looking at a mass spring system. So given this little diagram of the system, we have a mass of 0.3 kilograms that's on a horizontal spring. I believe we're told that the surface here is frictionless. So we have no friction to consider between the block and the table, the horizontal surface. And we're given this graph of velocity as a function of time. We're told that this block is displaced to the right and then released from rest at time t equals 0. Okay, so the first question, we're asked to find an equation for the velocity with all numerical values for constants inserted. So we're going to use this graph that's given to us to find the equation. This is a sinusoidal graph, which means technically there is an infinite number of solutions, so we just need to find one of them. If we look at this, you'll notice this looks like an inverted sine graph since it starts at 0. So I'm going to look for an equation that fits that. So an inverted sine graph has a minus sign out in front, it has some amplitude a, and then it has some angular frequency omega. So we need to find the values for a and omega. A is just the amplitude of the graph. If I look here, that amplitude appears to be about 0.16 meters per second. So technically this would be minus a, and then this would be plus a at the other end. So we know a is 0.16 meters per second, so how do we find omega? Well, if you remember, the angular frequency is related to the frequency. It's 2 pi times f, which means it's also 2 pi divided by the period. The period can be read from this graph here. If I look at one complete oscillation here, this spans about 0.7 seconds. So that is my period t. So the angular frequency is 2 pi divided by 0.7, which is about 8.98 radians per second. So I can plug both of those values in, and I get Vt is equal to minus 0.16 sine of 8.98 t. All right, so that's part A. Part B wants us to find an equation for x as a function of t. All right, this one will be a little trickier since we're starting from velocity. But if you remember, there's a relationship between position and velocity. That is, velocity is equal to the derivative of the position function with respect to time. So if we reverse this, the position function will be the integral of velocity as a function of time. So let's just do this integral. I'll bring the minus 0.6 out in front. Oops. All right, so how do we integrate sine? Well, the derivative of sine is cosine. The derivative of cosine is minus sine. So we have the integral of sine that would be minus cosine. And that's actually going to cancel the other minus sign we have out in front. So we're going to get, as our integral, the cosine of 8.98t. And then we also have to divide by what's out in front here. Right. And that's because if you think about what you do when you take the derivative of a sine or cosine function, you would multiply by this coefficient that's inside that's given a result of the chain rule. So if we're taking the integral, we have to divide by that constant. All right, so we have 0.16 divided by 8.98. That's about 0.018 as our amplitude. All right, part C asks us to find the value of the spring constant K. Right. So for this, the easiest way to get this is just to look up our formulas and remember that the frequency of this oscillation is going to be determined by the mass and the spring constant. And that relation is that omega is equal to the square root of k over m. So if we rearrange this, m times omega squared will be the spring constant k. The mass is given as 0.3 kilograms, and then omega was 8.98 approximately. So that gives us a spring constant of about 24.2 newtons per meter. All right, so for the remainder of this problem, we're looking at a different experiment where now the block is on a rough surface. So let me pull in that picture. All right, so now we do have friction. I guess they don't really tell us anything about a coefficient of friction here because we're not doing any calculations with the friction, but we are asked some qualitative questions about how the motion here would differ. So for part D, we want to draw a Freebody diagram for this block in two different scenarios. Let me move this down here. Whoops. There we go. Okay, so we want to draw a Freebody diagram showing all the forces acting on the block in two different scenarios. So at each case, we want to show the system when when the spring is compressed at distance d. So the block is going to be at the location shown in the figure for both of these Freebody diagrams. It's going to be right here. The spring is compressed at distance d over 2. So the block is going to be to the left of equilibrium, but it's going to be moving to the right in the first case and then to the left in the second case. So what would these Freebody diagrams look like? Well, there's going to be vertical forces, gravity and the normal force from the surface. Since the spring is compressed, the spring is going to push the block to the right. So we will have a spring force here. And by the way, so far everything that I've said applies regardless of what direction the block is currently moving, right? So the spring force does not depend on what direction the block is moving or how fast it's moving. It only depends on how much the spring is stretched or compressed. So the only difference here is going to be friction. There will be kinetic friction, and it's always going to be in the direction opposite of the motion. So when the block is going towards the equilibrium position, it's moving to the right, so that would be the velocity, so that means the friction will be in the opposite direction. When it's moving away from equilibrium position, V is in this direction, so kinetic friction is this way. Okay, so a couple of points about the kinetic friction forces that I drew here. First of all, they should be the same magnitude in both pictures here because kinetic friction does not depend on things like the velocity. It just depends on the magnitude of the normal force, which will be the same, and the coefficient of friction, which will also be the same. What about in the first figure here? You'll notice I drew it lesser in magnitude than the spring force. That's because the block will still be accelerating as it's moving towards the equilibrium position. The spring is going to be losing potential energy. Some of that potential energy will be lost due to friction, but we're assuming that the block will continue speeding up as long as it's moving toward equilibrium and slowing down when it's moving away from equilibrium. All right, so the last part of this problem here asks us to sketch a graph of velocity versus time for the case where there's friction between the surface. So what I've sketched here is a graph of what velocity versus time would look like if there were no friction. So we would just have a sine graph as before. Here we're starting with different conditions. So the block's actually going to start initially moving to the right. So we have just a regular looking sine graph here. So how is friction going to change this graph? Friction is going to cause the block to gradually slow down and eventually stop. So what's going to happen is the amplitude of this sine wave is going to gradually get smaller and smaller. So I could draw something like this. So notice the amplitude gets smaller and smaller over time, and if this continued long enough, the graph would eventually become a horizontal line and the block would come to a stop. All right, so that takes care of the first problem. Moving on to the second one, problem 2 deals mostly with experimental design. So there's not going to be a whole lot for me to write down here. There's really no equations to work through. So I'll just mention a couple of the points that the viewers would be looking for a problem like this. So for part A, we want to choose a set of equipment to design an experiment that will let us test the conservation of energy. There's actually multiple potential right answers here. The two things you must have are a meter stick and stopwatch. We need some way of making measurements of distances and times in this problem, so we have to have the two measurement devices here. Any other combination of equipment would be fine as long as they're consistent with the rest of your problem, but you do need to include these two. Okay, part B says outline a procedure for performing your experiment. Again, there are multiple different experiments that you could set up here. A couple of examples that were given. You could set up something like a modified outward machine. We could put a cart on a horizontal tabletop and then attach a string to it, run the string over a pulley, and put a hanging mass there. So you're going to allow the potential energy of this mass to be converted to kinetic energy of the hanging mass plus the car. So by making measurements of how far the mass moves and how much time it takes the system to move, you could perform your experiment that way. Another thing you could do is just simply put your cart on a ramp, measure the time it takes to roll down the ramp, and measure how much kinetic energy it has at the bottom, how much potential energy it had to start with, and then see whether those are equal. All right. So some of the key things they're looking for here, you have to have something in your procedure that mentions a measurement of height in order to determine gravitational potential energy, and you have to describe some measurement of velocity. And then your diagram, since there was a diagram required for this, should show any measurements of height or distance that will be required. So if I was doing the cart on a ramp experiment, I should label this height here because I will have to measure that. And then I should probably also measure this length here because having that length measurement as well as the time will be crucial to determining the final speed of the cart when it reaches the bottom of the incline. All right. Part C asks you to give more detail on the calculations of gravitational potential energy and kinetic energy that would have to be made. Here you need to describe your measurements, or I should say calculations, of 4 key parameters here. So you need to show how you're going to measure the initial and final potential energy, and also the initial and final kinetic energy. These are worth 1 point each. And then you also need to describe how you're going to calculate the final velocity, or the instantaneous velocity of the cart when you want to measure its kinetic energy. And that is 2 points. So some examples of how you might describe this. If you are using the cart on the ramp experiment, forgive the very shoddy drawing here. When the cart reaches the bottom of the ramp, it's going to have some instantaneous velocity. So how do we get that? Well, if we know the length traveled by the cart and we know the time, we know that the distance traveled is equal to the average velocity multiplied by time, assuming uniform acceleration and an initial velocity of 0. The average velocity is going to be 1/2 the final velocity. So we can say the final velocity will be 2 times the length of the incline divided by time. So that would be like an example of what you would describe for that sort of experiment. Okay, parts D and E ask you to think about how you might analyze the data for this hypothetical experiment. So for part D, it says, after your first trial, your calculations show that the energy increased during the experiment. Of course, that should not happen, so we want to think about something that might have happened in the course of us conducting this experiment that would explain this. So, two possible example answers that come to mind here. You might say that the cart was pushed accidentally. This would give the cart some additional kinetic energy that you didn't factor into your calculations. So the kinetic energy initial would be greater than 0 instead of equal to 0, which you would assume in your calculations. So this would cause the energy to appear to have increased over the course of the experiment. Another possibility is maybe you pressed the stopwatch too soon. I guess pressed too soon when it's at the end of its motion. So this would mean the delta t that you measure was smaller than the actual value. So that's going to cause you to overestimate the instantaneous velocity and therefore overestimate the kinetic energy. So it's a couple of examples that you might suggest for part D. Part E says that now suppose that in your other trials, your calculations show that energy decreased during the experiment. So again, assuming you make no math errors, give some kind of reasonable physical explanation for this happening. And then it says include references to conservative and non-conservative forces as appropriate. So this one should actually be easier than part D. The easiest answer to go with here is friction. So, of course, you should give more than just that single word. So how would this explain things? If there's friction, that would cause some of the initial energy of the system to be converted into thermal energy rather than kinetic energy. So instead of just having initial potential energy being converted to kinetic energy, some of that is also becoming thermal energy. So your final kinetic energy will be less than you expect if there's no friction. All right, so let's move on to the third problem now. All right, so the third problem involves some rotational dynamics and kinematics here. So the problem here states that we have a hoop that is sliding across a frictionless surface, not rotating, just only sliding. So make that very clear here. Then eventually when it reaches this point, it slides onto a rough surface where there is some friction, and that friction is going to cause the wheel to start to rotate as well as slide. And eventually, after it travels some distance L, it begins rotating with no sliding, or we call this rolling without slipping, which means that there is now a relationship between the velocity and the angular velocity. So to start with, we have some initial velocity v0, and the angular velocity is 0, and then the angular velocity will start to increase as this thing rotates up, and by the time it goes through this distance L, we now have this equation here, v equals omega r, which will be satisfied. So we want to figure out the details of how exactly this works. All right, so let's look at part A first. So we want to use Newton's second law to derive a differential equation that could be solved later for first the linear velocity, then for the angular velocity. So for the linear velocity, we're going to use the linear form of Newton's second law. Net force equals mass times acceleration. Okay, so what are the forces acting on this thing as it's rolling through the area with friction? So there's going to be a weight force and a normal force in the vertical direction, and then there's going to be friction. All right, so friction has to cause this thing to start rotating clockwise. So friction has to be in this direction. So this friction is going to do two things. It's going to slow down the linear velocity, so v will actually decrease at the same time as it starts to torque up this wheel and cause it to rotate faster and faster. So while omega is increasing, v is also decreasing. All right, so moving back to this equation now, we want to be very careful with signs in this problem because we want to make sure we show negative accelerations when appropriate. All right, so I'm just going to define this to be my positive direction for everything. So my net force is going to be minus F, which since this is friction, it's going to be minus mu times mg. And then that's going to equal mass times acceleration, but acceleration is just the derivative of velocity. So I can cancel the m's, and I get derivative of velocity equals minus mu g. So that's my first differential equation that tells me how v is going to change with time. For the second one, I want to know how the angular velocity is going to change with time. So I need to use the rotational version of Newton's second law. All right, so here the torque is going to be the friction force multiplied by the radius of the wheel. The torque in this case is going to be positive. For rotation, I'm actually going to make clockwise my positive direction to make that consistent with the positive direction of forward motion. So my torque is Fr, the moment of inertia is given, that is mr squared, and then alpha, that's the angular acceleration, which is the derivative of the angular velocity. All right, so I can simplify this a little bit. I'll plug in F equals mu times mg again. So I get mu g divided by r is equal to d omega dt. Right. So notice I have the correct signs for both of these. dv dt is negative, that tells me that v is going to be decreasing. d omega dt is positive, which tells me that omega will be increasing. All right, so now in B, I'm going to take these equations and use them to try to find the actual equation for velocity as a function of time and angular velocity as a function of time. So let's look at the linear velocity first. All right, so I have a equation here that deals with derivatives. So if I want to get rid of the derivative, I will take an integral of both sides. What I'm actually going to do here is do separation of variables and move the dt over to the other side. So now I'm going to integrate both of these. Okay, so if I want this just as a function of time, I'm going to integrate t from 0 to some arbitrary time t. And then v is going to go from the initial velocity v0 to some unknown v, which is going to be a function of time t. All right, so I have limits of integration that are consistent on both sides. When the time equals t, velocity equals v of t. When time equals 0, the velocity equals v0. Okay, so now when I do this integral, on the left I get vt minus v0. On the right, mu and g are just constants, so the integral, I can pull those out in front, and then the integral of dt is just t. So this is my equation, or v of t is just equal to the initial velocity minus mu gt. So the velocity is going to go down linearly with time. For part 2, I'll do the same sort of thing with this equation above here for d omega and dt. So I can say d omega equals mu g over r times dt. And I will integrate both of these. Time will go from 0 to t. Omega will go from the original omega 0 to omega t. So I get something very similar here. Omega of t minus the initial omega equals mu g over r times t. Now I can also put in the fact that the initial omega is actually 0, so we get rid of that. All right, so here are our equations. Velocity starts at v0 and then decreases linearly with time. Omega starts at 0 and increases linearly with time. And then at some point we'll get an intersection of sorts between these where v of t is going to equal omega t times r. So that's what we're going to look at in the next part. Okay, so part C, we want to derive the time that it takes the ring to travel the distance L. So we know that after it travels the distance L, we have this condition being met that Vt equals omega times r. All right, so I'll write this after it travels the distance L, because of course this equation is not true for every value of t, it's true for some specific value of t that we're trying to find, so maybe I will write it like this. Okay, so I can just plug in the equations that we got in the previous parts, and then I'll just replace t with some capital T. All right, so the right-hand side, the r's cancel, and we just get mu g times t. All right, so v naught minus mu gt equals mu gt, so that means v naught equals 2 mu gt, or the time equals v naught divided by 2 mu g. All right, so this is the time that it takes the ring to travel the distance L. Next part asks us to find an expression for the magnitude of the velocity at this time. So we just take this and plug it into our equation for velocity. So it's going to be v0 minus mu g times this time value that we just solved for. So notice we get v0 minus 1/2 v0, which is just 1/2 v0. So velocity decreases to exactly half of its initial value by the time this thing starts to roll without slipping. All right, so now for part E, we want to derive an expression for the distance L. Well, L is the distance that this ring travels between time 0 and time capital T. So we can integrate from 0 to t our expression for velocity. So our limits go from 0 to, what was it here? v0 over 2 mu g, and we are integrating the expression v0 minus mu gt dt. Okay, so if we do this, we can write this integral as v0 times t, that's the first term, The second term is going to be quadratic. So t becomes t squared over 2. And then we will plug in t equals 0 and t equals v naught over 2 mu g. So there's a little bit of algebra here to plug things in and simplify, but you should eventually get 3 v0 squared over 8 mu g. All right, you may be wondering if there's an easier way to get the answer to part E, and turns out fortunately there is. Since the ring is undergoing uniform acceleration, we can simply say that L is going to be equal to the average velocity times t. So think about what the average velocity is. We're going from initial speed of v0 to a final speed of 1/2 v0. So the average is going to be 3/4 v0, and then t was v0 over 2 mu g. So if we plug those two values together, we get 3/8 v0 squared over mu g. And notice we get the same answer there. All right, so there's a little bit of calculus in this one. The main thing to understand here is that when we have rotating with no slipping, this equation here is the one that needs to be satisfied. And the twist here is that both v and omega are functions of time. So what we're really saying is this for some value of t. So what we had to do in this problem is use Newton's second law to figure out an equation of velocity as a function of time, and then an equation for omega as a function of time, plug those into this equation that I've just written in green, and then use that to solve for the time at which rolling without slipping takes place. All right, so I will go ahead and end the video here. If you have any more questions, as usual, please feel free to send me a message. Thanks so much for watching.